Hey, it's Dr. J. We've come to the end of the course, my friends. So we're going to conclude the study of pre-calculus and send you on your way to calculus next semester. But I can't let you go without covering parametric equations first. An interesting way of looking at graphs that you might have already seen before. So all of the graphs that we're going to show today you have seen before. Before I actually do any real problems, let me just give you the idea. The idea is if you have a rectangular, or what's called a Cartesian equation in two variables, typically x and y. Something like, I don't know, something very simple that you learned in basic algebra, like y equals 2x plus 4. Well, this equation is essentially a function, and we say that y depends on x. And it has various different notations. One notation is f of x. You could say y is equal to f of x, or f of x is equal to 2x plus 4. So we're essentially saying that every y value depends on the x value. So you're plugging in x's to get y. Yeah? So for example, if you plug in x equals 0, so f of 0, you would get 2 times 0 plus 4, which is 4. And so we would say that this is the point x equals 0 and y equals 4. Yeah. But that point is sort of static. It's fixed in time, and it was dependent upon what the value of x was. And so you could do this for various points. Let's plug in, I don't know, x equals 1. No reason to get too crazy with it. Plug in 1, we would get 2 times 1 plus 4, which is 2 plus 4. So that would give us y is equal to 6. So we'd have the point 1, 6. Okay. And so the graph would be 0, 4, 0, comma 4, and 1, comma 6. And we would have this graph. And so that would be the graph of the line y equals 2x plus 4. And then this is where it gets weird, okay? In mathematics, in calculus, even sometimes in algebra, or especially in advanced algebra, we think of the line as actually moving over time, right? You do this probably in physics as well. You'll think about an object actually moving through time. The problem with using this equation to represent movement is this graph is not moving. Or I should say it's not really moving. All right. If I put an arrow on here, I'm basically implying that the graph is moving in this direction. Yeah. And then sometimes you put an arrow down here, and that sort of implies that the graph is moving in that direction. But these arrows are not really telling you the truth, because these arrows are just figments of our imagination. It's not actually moving over time. What's actually happening is this. The reality is this. It's kind of like a box of pictures, you know. I know I'm not really going to break out a box of photos, but you could think of each dot as simply a, some sort of box of photographs. And if you sat there and flipped through a series of photographs, right? So you start 0, 4, 1, 6, 2, 8, 3, 10, then you would get the illusion and that's the way a motion picture works, right? You're flipping through a bunch of pictures very, 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 very fast. In fact, that's what I am right now. I'm not, well, I guess I am actually moving, but you're just seeing a whole bunch of pictures flashing at you. And so if you had a box of these sort of photographs, they're not really photographs, they're points, but I'm using the word photos as sort of a graph. Get it? Photograph. Graph means draw, right? Photo means to sort of draw with light. So I would just be looking at these points, and it would be our imagination that would be putting these things together, and we see the illusion of movement. Okay? Well, what if we don't want it to be an illusion? What if we want this graph to actually move over time? Right? What if we added in another variable called a parameter? So t is called a parameter. All right? It's usually thought of as time. And so what if I were to say, well, when t is equal to 0, where am I? Or where is the point? Which of these points are you at when t is equal to 0? And that would give us sort of the idea that, well, maybe when t is equal to 0, maybe you're starting way down here in quadrant 4, and maybe it's a point that's not even in this graph. Yeah? So maybe the points that I picked out were not necessarily representative of the time in which this graph is moving over time. So I could say, oh, when t is equal to 0, maybe my x and my y are at -6 and -8. And then what if when t is equal to 1, I'm at -5 and -6. So maybe I could think of time like a clock, and over time, what's going to happen is each time I plug in a different value of t, the graph will move over time. And now the movement is based on time. In other words, I mean, it's less of an imagining it moving, like what you would do with a box of photos. With a box of photos, you just sit there and flip through the photos, and your brain kind of connects the photos together and says, yeah, I can imagine that I've moved from point A to point B because, I can see the photograph. Maybe you did this when you were a little kid. You take a pack of sticky notes and you flip through the sticky notes, and it makes it look like the little man is walking, or sometimes you draw a picture of a ball bouncing or something like that. But if I were to put these together with a parameter over time, as t moves through time, I'm not only imagining that the line is moving in a particular direction, but I'm actually generating a line with respect to time. And so that would mean that instead of y depending on x, we would say that both x and y depend on t. And this is called a parametric equation or a parametric system. It's usually a system of equations because you need one equation for your x and another equation for your y. Okay, so that's the basic idea. The line is still the same line, right, that I drew a minute ago. It's just this line is actually moving over time. So let's see an actual example. I think the hand waving is not as useful as actually showing the system. So consider the parametric equations. X of t is t minus 6, and y of t is 2t minus 8. All right, we're going to let t go to infinity, and we're going to assume that t is greater than or equal to 0. So we're not going to go backwards in time. We're going to start at t equal to 0. This is sometimes called the initial point. So x of 0, what happens if you plug in 0 for t? It's going to give you my initial x value. So that'll be -8. And y of 0. Oh, I wrote one of these equations down wrong. That's supposed to be a 6. Sorry about that. I was writing too fast, and those are both not supposed to be 8s. So for the x, it's a 6, and for the y, it's an 8. I'm glad I caught that now before I got too far into it. So this is the initial point. If t is equal to 0, then x is equal to -6, and y is equal to -8. So my graph is going to start way down here at, it's the same one I just mentioned earlier. I just am being a little bit more precise about it this time. 1, 2, 3, 4, 5, 6, 7, -8. So it's as if the movie starts right here. This is your initial point. Okay. You need to plot at least 2 points to get the line, but I'll show you several points. In your homework, I'll make some modifications to this so that you can do it a little easier. Let's plug in x equals, let's plug in t equals anything greater than 0. Let's skip to 3, just to kind of get the movie started. We'll skip ahead a little bit. So we got 3 minus 6. That's going to be -3. And y of 3 is going to be 2 times 3 minus 8. 6 minus 8, which is -2. So when t is equal to 3, our point is -3, -2. So here we're at t equals 0. We're going to skip ahead to -3 and -2. And now the arrow is not just a figment of our imagination. It's actually, at least mathematically, actually, nothing is really happening. All of this is in our mind anyway. But in terms of mathematics, as you move through time, going towards infinity, this graph will be moving from left to right. Let's plot a couple more points. Let's do x of, I don't know, 6. So that'll be 0. And y of 6. So both x and y depend on t. So that'll be 12 minus 8, which is 4. So when t is equal to 6, X and Y are 0 and 4. Okay. So this would be the graph of the line. And we would say its orientation as t goes to infinity, this graph goes from left to right. So we'd say this has a left to right orientation. Now, here's the deal on the homework. The homework makes you just draw a straight line. So what your line is going to look like on the homework is it's going to pass right through all of these points on the homework. And it's just going to extend all the way off the screen to the left and all the way off the screen to the right. I recommend plotting t equals 0 and then one other point. So just pick, plot any 2 points on the homework. All right. You don't have to do as many as I did. You do at least 2, or any 2 that you like. I always recommend starting with 0. All right. So be careful with the orientation. Sometimes if your first point ends up here and then your second point ends up down here in the other quadrant, if these arrows are going the other way, then that would be right to left orientation. I'll do an example of that in a second. I'm going to show you next, before we move on to the next, how to eliminate the parameter t. So how do you get rid of t? So how do you get rid of t? Well, the first thing you do is you rewrite the equations as simple equations. So the first thing you do is you eliminate the function notation and just write them as x and y. Okay. And now you solve one of them for t and then substitute into the other. So you're basically going to solve this just like you did a system of equations. So let's go ahead and solve this. We have x equals t minus 6. That means t is equal to x plus 6. Just adding 6 to both sides. It gives us our t. And then we're going to substitute it into the other equation. So we have y equals 2 times x plus 6 minus 8. So I'm taking this equation here, y equals 2t minus 8, and I'm substituting it. And then I'm going to simplify. And there's that original problem that I just explained. So this is called the Cartesian form. So we have the parametric form. Parametric form involves the letter t, the parameter t. And you have the Cartesian form, which is only x and y. The Cartesian form is the line without the arrows. Yeah. So you can't tell which direction it's going when it's in Cartesian form. Let's try another example. Let's try another example. And so we're always assuming that t is going towards infinity and it's greater than or equal to 0. There are some problems that you might see after this course where they use a parameter that goes into the negatives. You might start at -1 or -2 or something like that. But typically, I like to start with 0. I think of it like a stopwatch, right? When you click start on a stopwatch, you begin timing something or filming something, that's always 0. Everything starts at 0. Even if there was stuff going on before you click start. So this is assuming well, I don't know what's going on before time begins. So just keep that in your back of your mind when you're calculating it. All right. I like to start with my initial point. So x of 0 will be 2. And y of 0 will be -4. So I have the point 2, -4. So when I draw my graph, I'm starting over here at 2, -4. Okay. Now I'm going to plug in another value for t. So if you just want to be lazy, you can just plug in 1. It's OK. There's no reason to kill yourself over it. So I have y of 1. Y of 1 is -4. Minus 3 times 1. So that'll be -7. I'm glad I didn't go much further because look where I put my graph. It's going down to the left. So therefore, as t goes to infinity, the orientation of this graph is right to left. So this graph has a right to left orientation. This was my t equals 0 point, and this is my t equals 1 point. And so the graph is going through from right to left. I'm kind of regretting having drawn my axes the way I did, because now I have all this empty graph space here. This is the way it will look on the computer. When you draw this graph on canvas, you're just going to draw a straight line, and it will just look like that with 2 dots. OK. I tried and I tried again to get this piece of the line to disappear. And I could get it to disappear. You might have noticed the homework pop up, and then I pulled it back because I was trying to make some corrections to it. But every time I got this piece of the line to disappear on canvas, it kept marking the answer incorrect. Even though it was correct according to my definition, the computer just wasn't reading this as being correct. So in order to get your graphs on canvas to mark correct, just draw a straight line, and the orientation of the line is just based on the value of t. So as t goes to infinity, pay attention to what direction the line is actually moving in. Okay. And again, if you want to rewrite this into eliminate the parameter, if you're asked to eliminate the parameter, you're just going to use substitution. So you're going to go x equals 2 minus t. Let's go ahead and, how should we do this? Let's do plus t. And then minus x. So there's your sub. And then now take your y equation. You got y equals -4 minus 3t. And sub this guy in for t. You always want to do x first and then sub it in So solve t in terms of x, sub it in so that your equation is in standard function form. Y minus 3 times 2 minus x. There's your sub. And then now simplify this. And put it in slope-intercept form. And so this would be your slope form. In terms of a function, you could say f of x is equal to 3x minus 10. Or here's a new notation you might not have heard or seen before. Y of x. So there are two different versions of function notation. You could say f of x, 3x minus 10. But another type of function notation is just not to use the letter f, but just to keep it written as y. Okay. So basically, these three answers are all this exact same line here. Y equals 3x minus 10. All right, well, that's the basic introduction to parametric equations. Example 3, find a system of parametric equations that models a point moving in the xy plane such that when t is equal to 0, the point is -5 and 7. And when t is equal to 5, the point is -4 and 5. So let's draw a rough sketch of what we want. We want a parametric equation that starts over here at -5 and 7 when t is equal to 0, and then moves over 1 unit to -4 and down 2 units to -5. And it's going to do that over the course of 5 seconds. I guess you can think of t as being seconds. So starting at 0, you're here at -5 and 7. And then after 5 seconds or 5 whatever units of time you're measuring in, I usually think of them as seconds because it's like a movie. In fact, a movie is probably more than a second. It's like a tenth of a second or something between each successive frame. Okay. So you want to find a system of parametric equations. So we want to know what is x and what is y in terms of t. That's the system of parametric equations. Now this is a line. All right, so since it's a line, okay, we can assume that x is AT plus B. So this is a linear equation. I always recommend solving for x first. Once you've solved for x, you can plug it back in to figure out the y. It turns out that you can do it either way. But you've been trained since a young person, probably 12, 13 years old, to solve for x. So I just want to stick with what you've been trained to do. And we typically think of functions as functions of x anyway. So this is a function of t. All right, x is a function of t. All right. So what do we know? We know that at t equals 0, x is negative 5. So that means, now I don't want to substitute x to be negative 5. I want to figure out what is b and a. All right, a and b are the unknown values that I'm trying to figure out. I know x, and I know t. I'm trying to figure out a and b. Yeah. So I know t is 0. Right? And I know x is negative 5. So I'm not solving for x. I'm solving for a and b. Well, that finds b pretty quickly. Yeah, so I know b must be negative 5. I need to use this space here. So now I know that b is negative 5. So now we have x is equal to at plus negative 5. I still don't know who a is. I typically write at minus 5 instead of plus negative 5. At minus 5. I still need to figure out who a is now. I got b. I need a. But I have another point. Yeah, I've got another point. X is negative 4 when t is 5. So put in negative 4 for x and put in 5 for t. All right. I need to erase this graph. I'll reproduce the graph when I'm done with the problem. So now I've got negative 4 equals 5a minus 5. Or in other words, if I add 5 to both sides, I get 1 equals 5a, combining the negative 4 and the positive 5. So a is 1/5. There's my a. All right, so now we know x as a function of t. It's going to be 1/5 a minus 5. Because my b is negative 5, and my a is 1/5. Oh, sorry, it's 1/5 t minus 5. Sorry about that. A is 1/5. I almost wrote 1/5 a. That would be a mistake. Okay. All of your work should be put into finding the parameterization for x. Once you find the parameterization for x, finding it for y is going to be much easier. All right, so we got x. All right, so what are we going to do for y now? Well, we're going to do the same basic idea, at plus b. Now remember, I erased it, but we had at t equals 0, it was negative 5 and 7. And when t equals 5, it's negative 4 and 5. So this time we're focusing on the y values. You might notice a pattern here. When t is equal to 0, the b is automatically going to be whatever the y value was for the initial point. So this always happens when t is equal to 0, whatever the y value, that will automatically be your b. Okay. Now to find the a, well, we know that b is 7. So we can say AT plus 7, just copying this here. And now use the other point. 5 is equal to A times 5 plus 7. And now you're going to solve it exactly the same way you solved for x. I guess in hindsight now I could say it really doesn't matter which one you do first. My way of doing it is to always find the x first and then go back and find the y. So your A is negative 2/5. So now my y of t is negative 2/5 t plus 7. So this is my system of parametric equations. I erased the graph a long time ago, but we could easily reproduce the graph. It's pretty easy to check what you got. You could use these to check. Yeah. X and Y. Go ahead, you can do it with mental math. Plug in 0 for t into both of these, and you're going to get negative 5 and 7. Check. Negative 5 and 7. Negative 5 and 7. Check. All right, now plug in 5 for t and see if you get negative 4 and 5. So plug in 5 for t. 1/5 times 5 is 1. 1 minus 5 is negative 4. Check. All right, now for the y value, plug in 5 for t. Negative 2/5 times 5 is negative 2. And then negative 2 plus 7 is 5. Check. And the orientation as t goes to infinity is left to right. So this graph is moving in this direction from the left to the right over time as t goes to infinity. And again, I'll just say it one more time. If you were to draw this on canvas, it would just look like a straight line. Right? And you would even see the past. The line would go off into be the ghost of yesterday, although the graph technically starts right at this point here. This is your t0, t equals 0 point. So that's when the movie began. Yeah, the parameterized movie. Okay, so that's the basic introduction to parametric equations. I think if you understand the way lines work, it's kind of walking through the footprints of your past education. You always learn lines first, and then you might have moved on to some other types of equations. So let's go ahead and graph x of t is 2 cosine t, and y of t is 3 sine t. Okay. I'm going to give you a limit on what t can be. Just anytime you see sine and cosine, it's pretty common to stay between 0 and 2 pi. Although there are other examples that get elaborate, maybe in calculus or something. But for our particular setting, we're just going to do one rotation. Okay. You could do this with mental math, or you could sort of make a chart you have t, you have x, and you have y. All right. So 2 cosine of 0. That'll just be 2. Yeah. 3 sine of 0. That'll be 0. So our graph starts at 2, 0. Okay. Let's do, I don't know, pi over 4 or something. Okay. So what's cosine of pi over 4? Cosine of pi over 4 is root 2 over 2. Yeah, I'm doing this all with mental math. If you want, you can use your calculator. Did I even bring my calculator today? So you could do cosine pi over 4, which would be root 2 over 2. And then multiply it by 2, you're going to get 1.4. That's good enough for me. Now for y, you're going to do sine of pi over 4. That's also root 2 over 2. And then you're going to divide it, or you're going to multiply it by 3. So if you want to show all the work, it would be root 2 over 2 and then all times 3. I don't have enough room in this little chart to do that, so I'm just going to do it on my calculator here. So I've got root 2 over 2 times 3 is 2.1. So this point at pi over 4 it's kind of like polar. I mean, you can think of this very much like a polar graph where t is acting like theta. Yeah. Which, by the way, time is like an angle if you really think about it. Think about an old clock. As time goes on, what's happening? The hand is moving around the clock. That's theta. That's an angle. So time is an angle. Right? It's also the Earth going around in a circle and going around the sun. So the concept of time and a circle is, it goes back to time immemorial. So you've got 1.4 and 2.1. I'm going to try to draw my graph to scale. So I've got 1.4 and 2.1, so right about here. Okay. Let's skip to pi over 2. At pi over 2, cosine of pi over 2 is 0, and 2 times 0 is 0. Sine of pi over 2 is 1, and 3 times 1 is 3. So now we're here at 0, 3. It's almost a circle. Yeah, it's not exactly a circle because this is 3 and this is 2, so it's not exactly a circle. All right, and so what we're going to do is we're going to continue to do this. 3 pi over 4. You're going to get negative 1.4 and 2.1. So it's just trust me, if you want to work it all out, you're going to end up with a point right over here. It's basically the mirror image of this point. I hope that makes sense because we're using sine and cosine. So now that I'm at 3 pi over 4, the cosine is going to be negative, so the x value is going to be negative. By the time I get to pi, the cosine is going to be negative 1, so this will be negative 2, because it's 2 times negative 1, but the sine is still going to be 0, and so it's like the top half of an egg. Yeah, so this looks starting to look like an ellipse. All right. And you can continue as time goes around. This graph is going to continue to go around counterclockwise. So the orientation is counterclockwise. It's going around counterclockwise. I didn't finish the table. I'll leave it to you to finish the table. I stopped at pi, but I wanted you to go all the way to 2 pi so you can finish the table. DIY. You can do it on your own. You're not going to be too surprised that you're just going to get the same numeric values. Just in quadrant 3, they'll all be negative, and then in quadrant 4, the x's will be positive and the y's will be negative, and you know your basic sines and cosines. Okay. So this is an ellipse. I'm not sure, I never know how much you've seen of ellipses before, but the Cartesian form, to eliminate the t, it's easier to see that it's an ellipse. So let me just show you, but we're done with this problem, but I just want to show you, in case you've never seen the equation of an ellipse, maybe you can see it now. So you have x is 2 cosine t, y is 3 sine t. So x squared is 4 cosine squared t, and y squared is 9 sine squared t. So you have x squared equals 4 cosine squared t, and y squared equals 9 sine squared t. We're going to divide the x squared by 4. We're going to divide the y squared by 9. And then we're going to add these guys together. So we're going to have x squared over 4 plus y squared over 9. So we're going to add these guys together, and that's going to be cosine squared plus sine squared. And then we're going to use a trig identity. And this is the equation, or what's called the Cartesian form of an ellipse. Yeah. X squared over 4, y squared over 9. This is exactly the ellipse that we just saw. I always forget if ellipse has 2 L's. I don't know. Is it 2 L's? It might be. I don't know. Same thing with eliminate. Does eliminate have 1 L and ellipse have 2 L's? I don't know. I don't have my spell check. I'm not going to stop recording now. I think this was actually example 4. Example 5, eliminate the parameter, then graph. Yeah, sometimes, I mean, if you're really experienced in graphing algebraic equations, you see a parametric equation, you might want to just rewrite it as an ordinary equation and then graph it. So let's do e to the 3t and e to the 2t. Because if you saw this parametric equation and you'd never done it before, you might be sitting there plugging in values of t and getting dots all over the place and having a very difficult time understanding what's going on. So sometimes it's nicer to get rid of the parameter and then see what happens. So we're going to say x is e to the 3t, y is e to the 2t. Sometimes we just write the equation like this from the outset, and we don't put it in the function form. I just want you to understand the function form, because you're definitely going to see it next semester. And now you want to solve these guys using logarithms. So if x is equal to e to the 3t, well, then that means ln of x is 3t. And this one means ln of y is 2t. So just rewrite it into logarithmic form. Or take the log of both sides, if you like, the natural log of both sides. So now you have ln of x equals 3t and ln of y equals 2t. You're trying to eliminate the parameter, so you want to get rid of t. So we're going to divide both of these by 3. Divide both of these by 2. And since these are both equal to t, that means they must be equal to each other. Yeah, so you can eliminate the t by setting them equal to each other. Yeah, that's another form of substitution. Yeah. If this equals t and that equals t, well, then those have to equal each other. Yeah, so you've now eliminated the parameter. Now you want to simplify this equation. ln of x over 3 and ln of y over 2 is the same as 1/3 ln of x and 1/2 ln of y. But we studied natural logarithms quite extensively, so you know that that 1/3 and the 1/2 really just become exponents. And now you have exponential equations. And now you can take e of both sides, put the e back in, cancel the logarithm, and you get x to the 1/3 equals y to the 1/2. Sometimes people skip this step. Once you have log of x 1/3 and log of y 1/2, you can just jump directly to this step, right? Because note, if ln of a is equal to ln of b, then a is equal to b. So you are allowed to just jump directly to this step. But now you want to square both sides to get y by itself. And so you get y is equal to x to the 2/3. Since it's a function, I'm going to say y of x is x to the 2/3. This means the same thing as f of x. Yeah. Sometimes I like to just put it under here. Yeah. In basic algebra, you would say f of x, although that's probably not basic algebra. It's probably like, intermediate to advanced level algebra. What's in the box here is the way I want you to put the answer on your homework. Okay. Not sure if you've ever seen this graph before. It's the x to the 2/3 power. It's sometimes called the Gullwing graph. Yeah, looks looks like that. Have you seen that before? You could plug in a few points. 0. What would the value be at 0? It would be 0 to the 2/3, which is equal to 0. 1 be 1 to the 2/3, which is 1. That would be 1, 1. And then over here at -1, be -1 to the 2/3, which would be the cube root of -1 squared, which is the cube root of 1, which is still just 1. Let me make my graph look a little bit nicer. And why are they curved? Well, because they're nonlinear. These are curved radical graphs. So give them the shape, the same shape as a square root graph, but it's like, imagine one square root graph going to the right and another square root graph going to the left. And so this is x of t is e to the 3t, and y of t is e to the 2t parametric. Now, again, the parametric equation depends on t, so not both of these arrows can be true. If t is going to infinity, then these arrows would be going to the right. So you can imagine it coming in like this, bouncing, and then coming back up and going that direction. A parametric equation can't go two different directions, right? It depends on t. So that's the main difference between a parameterized equation and a Cartesian equation. Notice that these are quite different. They look quite different from each other, but they both have the same basic shape. Let's try another one, example 6. So 8 square root of t times 2t minus 1. Let's eliminate the parameter and then graph. So, same basic idea. Get rid of your t. First, I just get rid of the function notation. You can't just cross out the t on the right-hand side. That's too much of a leap. All right. Pick one of these equations and solve it. I usually pick x first. So I'm going to square both sides. So I'm trying to get t by itself. And then once I have t, I can plug it into the other one, and that'll eliminate the parameter. So this is my sub, and now I'm going to sub it into here. So I've got y equals 2t minus 1. This is going in for t. And that's it. So here we go. This is our answer. In function form, you could say f of x, or in this section we're using the notation y of x. 1/32 x squared minus 1. I don't know if you recognize this. It's a parabola. I sure hope you recognize it. Hardly ever do you have a 1/32. That just means the parabola is very wide. Yeah. Remember, if the leading coefficient is a very small number, it's been stretched out horizontally. If this was a number bigger than 1, then it would be stretched vertically like this. Would be very tall and skinny. I'm just going to move these over a little bit so I can draw my graph. So if x is 0, I'm just going to do this with mental math, all right? This is a parabola. This is the last day of pre-calculus. So plug in 0 for x. You're going to get -1 for y, right? That's your vertex. All right. What else could we plug in for x? Let's plug in, I don't know, something like 4. Or actually 8. Let's go to 8. Why did I pick 8? Because 8 squared is very nice. All right, what's 8 squared? 64. What's 64 divided by 32? 2. What's 2 minus 1? 1. So this would be 8 and 1. Like that. So x is 8 and y is 1. It is a parabola, so that means if you come over here to -8, it should still be equal to 1. Right. Again, I don't have to show that. -8 squared is 64. 64 divided by 32 is 2. And then 2 minus 1 is 1. So this y value is 1. All right. Now remember, the arrows can't really go both ways. Right? So you kind of want to think about the orientation. As t goes to infinity, what's happening to this? Is it going from left to right, or is it going from right to left? So you can use the parametric equation, plug in 0, yeah, and it's going to start here. And then as t goes to infinity, it's going to go to the right. So this would be the point as t equals 0. Maybe you want to plug in t equals 1. That'll put you right here at t equals 1. So over time, this graph is going to go from left to right. In fact, technically, if we're not allowing negative time, technically the left side of the parabola doesn't exist. Unfortunately, on Canvas, it will not let you graph just half of a parabola. So even though this half doesn't really exist, you still have to draw the entire parabola, keeping in mind that the orientation is from left to right. So keep in mind, as time goes forward, this graph is going from left to right. Okay, so we are very close to being done. Okay, our last example today will be number 7. So again, we have a trigonometric set of parametric equations. So it's both parametric and trigonometric. And we're going to let t range from 0 to 2 pi. Now, I did one of these similar problems in a previous example, and I made a big table of t's and x's and y's, and to give you the idea of how to figure out the orientation. We're going to try a different approach this time. I'm going to eliminate the t and then graph using only x and y. In other words, the Cartesian form. So just whatever it would have been in Cartesian form, and not really worrying about, point 1, point 2, point 3 going around in circles like that. I think I just gave it away. I just want to show you one more time how to eliminate the parameters. So we're going to rewrite this as x equals 3 plus 4 cos t. And y is -1 plus 4 cos t. And we're going to solve this for, or eliminate the t. Yeah. So we're going to subtract 3 from both sides. Then we're going to divide by 4. Then we're going to square both sides. And then we're going to put that on hold. Come over here and do the same thing with the y's. Add 1 to both sides. Divide by 4. And square both sides. You might as well just chalk it up to memory. Sines and cosines, you're always going to be squaring both sides. Oops. I said sines and cosines, and then I only wrote cosine. These are all sines. So these are your sines, your y's are sines, and your x's are cosines. So this is a classic trick to eliminate a parameter involving sines and cosines. You always want to use the Pythagorean identity. I don't want to lose these, but I need to erase them. So let me just write them up here for safekeeping. Now I can erase and get my space back. All right, so now we're going to take these guys and we're going to add them together. So we have x minus 3 over 4 quantity squared. Leave it in that form. If you actually start squaring it out, you might regret it. Plus y plus 1 over 4 squared equals, and now add your right-hand sides, cosine squared plus sine squared, and that's just going to be 1. Okay. Now, I don't want you to do too much simplifying here. I want you to do a little bit. So let's just do this. Just to make it look a little bit nicer. And then we're going to multiply everybody by 4 squared. If you prefer, you can just write that as 16. It means the same thing. I personally like to leave it as 4 squared, and you'll see why in a minute. X minus 3 squared plus y plus 1 squared equals 4 squared. Now you can see it's a circle of radius 4. Yeah, 4 squared. Yeah. Or you could say 16 instead of 4 squared. The problem with that, and maybe it's just unresolved issues from my other classes, whenever I say 16, I get students that will say the radius is 16. Or sometimes they'll say the radius is 8. So, but when you write it as 4 squared, I think it's clear that the radius is 4. If you want to keep that in mind, it's the square root of 16 becomes 4. And the center is positive 3 and negative 1. Remember, the horizontal and vertical shifts here are the opposite of the x's and the y values here. Okay, just a little quick review of algebra. So now when you draw your graph and go over to 3, and down -1, and then your radius is 4. So I'm going to go 4 units up. Which puts me here. I'm going to go 4 units to the left. Puts me over here. 4 units down. 1, 2 through -5 down here. And 4 units to the right. 2, 3, 4 over here. And it might not look great on the screen, but that should be a circle. Okay. So there's your circle. On your homework, you only need to plot 2 points. Just plot the center and then 1 other point, and then draw the circle with your tool. It'll be like a little circle tool that you'll use. Now, you better hang on to the original equations because that's going to tell you your orientation. Just plot 2 points. So pick 2 values of t, and then determine which way it's going. All right. I recommend starting with 0. All right. So what is a cosine of 0? That would be 1, right? And then that would be 3 plus 4, so that would be x is equal to 7. So you're right here. Three, 4, 5, 6, 7. So x is equal to 7. You're right here. Now plot 1 more point. If that point goes counterclockwise, which it probably does, because most of these trig functions go counterclockwise. If that point goes clockwise, then just denote it either way. The most common is counterclockwise. So pick an easy number like pi over 2. So cosine of pi over 2 would be 0. So 3 plus 0 put you here at 3. All right, and then now do sine. Sine of pi over 2 would be 1, and then 4 times 1 is 4, and then plus -1 is 3. So that puts you here. And so your orientation is the most common orientation is counterclockwise. It turns out in order to make a trig function go clockwise, you have to let t go the other way. Yeah. So pretty much all your trig graphs, sines and cosines, are going to go around counterclockwise unless you do some modifications to the values of t. Okay, it has been my extreme pleasure and honor to serve you. I wish you all the best in calculus. This course has concluded. Your final exam is next Thursday, May 21st. Do your homework. Dr. Jordan, signing out. Have a great summer.